Hi, this is Professor Fernandez. We are going to work on class note C in lesson 11. So for this example, I want to show that this set W I want to find a basis, I should say, for W. I already know that it's a vector space based on previous work that we've done. And this is a now much more familiar set to us that we've been working for so long in the course in differential equations. So what are we going to do? Well, we want to find a basis, right? Remember, basis means a subset, if you will, of the elements here, which are functions, that is linearly independent and spans the space. Great. And then we're going to use that basis to determine the dimension. All right, so what am I looking for? I am looking for particular functions in the space that span the space and are linearly independent. And what is this space telling me? This is literally the space of functions that solve this ODE. So this is an ODE that we know how to solve, right? Putting it into standard form, back from the first few lessons of the course, this is a first order linear homogeneous ODE, and we can solve that using the methods that we learned back in lesson 1. But I'm going to go back here and just remind you how that works. So what do? So I write this as dy over dt equals y, and then I would divide by y. And then the left-hand side is the derivative of the natural log of y of t. Okay. And then I integrate both sides. So I'm doing things a little quickly here because we did this back in lesson 1. I integrate both sides and I get t plus some constant c. And then I exponentiate both sides and I get e to the t plus c. And then writing e to the c as k, I get k e to the t. All right, so what I've just reminded you of is that the general solution to y prime equals y is y of t equals k e to the t. All right, so what do I mean by general solution, right? This means that every solution to y prime equals y can be written as k e to the t. So that's the first thing, right? If you listen to what I just said and think of it as, and put on your linear algebra hat, this shows that y1 equals e to the t spans w, right? Because of what I just said, every solution to y prime equals y can be written as some, quote, linear combination. In this case, it's not really a combination. There's no other function, but can be written in terms of a linear combination of y1. Great. So the second thing we need to do is we got to show linear independence. So this one's going to seem kind of silly, but this is, in fact, how you do this in general, which we've been talking about for a while. So for linear independence, we only have one function that we want to show is linearly independent. So if we just follow our definition for linear independence, we would do C1 times that quantity. We would set it equal to the 0 element in the space, the 0 function. And then this needs to imply that all of the C's constants, in this case, just one of them, is 0. So is this true? Well, so we can work it out here. So y1 is e to the t. So I'm setting up this equation. And then just realizing that e to the t, the exponential, is never equal to 0, right? It's always non-zero. Tells me that, yes, indeed, this equation implies that C1 equals 0. Okay, so y1 equals e to the t is linearly independent. Again, it seems a little silly, but it's important that it is linearly independent and that we check, because again, not every set of elements of a space are linearly independent. Okay, so since y1 of t equals e to the t is linearly independent and spans, I believe it's w, I'm going to scroll up here, yes, I called it w, and spans w, then it is a basis for w. Great. And to find its dimension, we find we just count the number of elements in the base. There is only one element here. So we would say, and the dimension of W equals 1. And that's it for this example.